Now we're going to focus on dipole-dipole interactions. Now, these interactions are stronger than London dispersion forces, but they're weaker than our hydrogen bonding or our ion dipole interactions. And the difference between these and our London dispersion forces is that it's still a dipole moment attraction between two molecules, except now the dipole moment is not temporary. It's not spontaneous. It's something that is inherent to the structure of the molecule. And so this takes place between polar molecules. And going back to the previous class, we determine if something is a polar molecule by evaluating its 3D shape and comparing the difference in electronegativity values of each of the bonds and using that to determine if it's an overall polar molecule. And that polar molecule means that there is an uneven distribution of electron density across the map, if you will, of the molecule itself. And so it happens with these dipole-dipole interactions or forces, intermolecular forces, is that the molecules will line up preferentially in space. So that way the partially positive end of the molecule will interact with a partially negative end of a different molecule. And so they'll kind of like naturally line up that way. Now, the intensity or magnitude of these interactions will increase as the strength of that dipole moment increases, or as you decrease the distance between the molecules. So in a solid state, it would be a more intense interaction or a larger interaction. But even in a liquid, it can be still quite strong, especially if we have a very strong dipole moment. So here are some examples at the bottom showing space filling models of, here, let me draw it out for you. We've got a carbon double bonded to an oxygen, and that's creating our dipole moment. Otherwise, it's bonded to a carbon and on either side and 3 hydrogens. And so that partially negative end on the oxygen, because it's more electronegative, will line up with the partially positive end of that carbon bonded to the oxygen on another molecule. And we create this dipole-dipole interaction right here. And this right here is the exact same thing, just showing an electrostatic potential map, which is basically a way of mapping electron density. And it's showing that in these red areas that you have a partially negative charge versus a partially positive charge. Now I'm using that delta symbol right here to indicate partial charge. So that means we're still talking about interactions between opposite charges that are less than a magnitude of 1, right? So it's not even necessarily a plus 1/2 and minus 1/2 interacting. It can be even smaller than that, and they'll vary. And so that magnitude of charge is quite small. And remember, we're still looking at distances larger than you would see within a bond. And so these are fairly weak, especially compared to a bond. Let's look at an example. So I have a list of molecules here, and let's go ahead and determine which will have the strongest dipole-dipole interactions and rank them. So our carbon dioxide molecule is going to be nonpolar. And if you can't just see that by looking at the chemical structure, remember, you can always build a little bit of structure, think about it in 3D, and assess its polarity. So that's just using the skills that we covered in 161. If you need to brush up on them, it is chapter 7 in the OpenStax textbook. So we get this structure right here that's linear with a 180-degree bond angle. And these carbon-oxygen bonds are both polar. However, because they're pulling in opposite directions and they're 180 degrees apart, they cancel out and we have an overall non-polar molecule right here. Or I'll get rid of that arrow. So we have a non-polar molecule, so it's going to have possibly no dipole-dipole interactions. All right, Hcn, hydrogen cyanide. So this one is going to be polar. Looking at it, it's going to be a hydrogen bonded to a carbon, triple bonded to a nitrogen with a lone pair. There is a dipole moment between that carbon and nitrogen. It's an electronegativity difference of 0.5 in that bond. Now looking at our C2H6S, this is going to be another nonpolar molecule. And there's a few different ways to actually draw this molecule. So even before I draw it, I know that all of my carbon-carbon, carbon-hydrogen, carbon-sulfur, and sulfur-hydrogen bonds, these would all be nonpolar bonds based on the electronegativity difference between the atoms. That they're all going to be less than 0.5. So there's no arrangement that I can make that would create a polar structure. And then lastly, we have hydrogen fluoride, which I know is polar. And this is a simple Lewis structure. You just really need to compare the electronegativity differences of the two atoms, right? It's HF. And so that fluorine is at a 4.0 and that hydrogen is at a 2.1. So we have an electronegativity difference that's going to be of 1.9. So that's really at the far end of our like polar covalent molecules themselves, right? Like it's almost an ionic bond. And so when we look at this, then we have a strong dipole moment if we have a large electronegativity difference. So we only have two molecules that are polar, right? So let's just look for the strongest one first. And one has an electronegativity difference of 1.9 and the other has 0.5. And so this hydrogen fluorine has a larger dipole moment. And so this is going to be our strongest of our dipole-dipole interactions. Now we have two nonpolar molecules, and so we then only have one other one with a dipole moment or a dipole-dipole interaction that can exist between molecules. And so our weakest one will be the HCN. So when I'm considering how these interact, I'm not comparing how this molecule interacts with any of the other molecules. I'm imagining that I have a pure sample of just hydrogen fluoride or hydrofluoric acid, and just other hydrofluoric acid molecules are interacting with the one I'm considering. I'm not going to worry about how these interact with each other. That'll be the next chapter when we talk about solutions.